The truss used to support a balcony is subjected to the loading shown. So we have a truss here and it's used to support a balcony and it's subjected to the loading shown. So at point A we have 60 kilonewton, at point B we have 40 kilonewton, and this is supported to there is a pin support here and there is another pin support there, and the whole truss is acting essentially like a cantilever. It's like acting like a cantilever. Okay, so approximate each joint as a pin. So each of these joints, joint A, joint B, joint D, will be assumed a pin, and determine the force in each member. Members are AD, AB, BD, DC, and DE. State whether the members are in tension or compression. Okay, so to find the forces in the members, we're going to use the method of joints, where we write equilibrium equations at each joint. So starting from joint A, okay, we use method of joints. So joint A. So at joint A we have this joint A here, and if this is our x-axis and if this is our y-axis, right? So we have a 60 kilonewton load applied at joint A in the form of a concentrated force and in the negative y direction here, and then the unknown member forces. So we can assume that member AB is a tension member, so that's AB, and let's assume that, so these directions are assumed, okay, initially assumed. You can assume as a compression or a tension. So the direction of the force at the joint, applied at the joint, is the same, essentially the same with the direction applied on the member itself. So if we are talking about a tension applied at a joint, so that is equal and opposite to the tension force applied on the member, so that becomes a tension member. If you have compression on the joint, then that is, let's show here, so equal and opposite compression on our member. So this means that we have equal and opposite compression. So if this is, let's say this is member AD here, okay, so that's member AD here. So this force makes this member AD a compression member. So compression on the joint, compression on the joint, tension on the joint, tension on the member, compression on the joint, tension on the compression on the member, tension on the joint, tension on the member. Okay, right, so let's continue with our problem. So we are writing, so this is FAD and this is 45 degree with the horizontal. Okay, so our equilibrium equations are essentially, we have two equilibrium equations here. Some of the forces in the x direction will be 0 and some of the forces in the y direction will be 0, and these are the assumed positive directions for x and y. Okay, so let's see. So we have two components of this force AD, so this component and that component here. So if we write the sum of the forces in the y direction essentially equals 0, okay, now we're gonna have this FAD times sine 60. So this is FAD times sine 45 degree minus 60 kilonewton is equal to 0. So we can, using this equation, we can find FAD, and that is equal to 84.9 kilonewton. Okay, so based on that finding, we can now write sum of the forces in the x direction is equal to 0. So we have FAB, force FAB, minus the x component of FAD, so which is FAD times cosine 45 degree is 0. So that's FAD found from the previous equation. So if you substitute that into the new equation, you get FAB to be equal to 60 kilonewton. 60 kilonewton. And by the way, since we are finding positive results here for the unknown forces, then our initial direction assumptions will be correct, making FAD a compression member and making FAD a tension member. Okay, so we show compression. So C for compression and T for tension. Okay, T for tension. Okay, so let's continue with our problem and focus on joint B. So let's focus on joint B then. So joint B. Okay, so joint B. So at joint B, we have joint B here. Okay, let's move up and remember what our joint B is looking like. So we have joint B here, 40 kilonewton, and then this member, this member, this member. So 3 members at joint B. Okay. So the applied force, we have an applied force of 40 kilonewton. So that's 40 kilonewton applied force, and others will be, we have at FBC, unknown member force, and let's assume that this is tension, FBC tension, and FBD compression, and we have FAB here, and we found FAB actually, so that's 60 kilonewton. Okay, so writing equilibrium equations for this particular joint. So this is a free body diagram written at joint B. So it's really straightforward to find. For FBC is equal to 60 kilonewton, 60 kilonewton and tension, and FBD is equal to 40 kilonewton, and that's compression. So it's simply by observation. Don't need to write some of the forces in the x direction, some of the forces in the y direction. It's quite obvious here. Okay, so and joint B is okay. So we continue with joint D then. So joint D, so writing the drawing the free body diagram at joint D. So let's remember joint D are going up. Wow. So at joint D we have 1, 2, 3, 4 members. Okay, so we have AD, BD, CD, ED. Okay, so going down, and we have our so we have our joint D. Okay, so that's joint D here. So for our joint D we have a 40 kilonewton here, which is up here, FBD 40 kilonewton, and we have this one here, which is FAD, and we found FAD. FAD is equal to 84.9 in compression. Okay, so FAD, so here FAD 48.9 in compression. Okay, so that's 84.9 kilonewton, and the rest is the other two. So this will be FDE here, unknown, and at a 45 degree angle we have, so that is also 45 degree angle. So that one is FDC. So we have 2 unknowns here, and simply we're going to write an equilibrium equation over there. So what I will do, I will just to explain actually what I'm trying to do at this particular joint. I'm going to go and copy and paste here this particular joint D and show on the member itself. Okay, so let's assume that I'm having cuts here. Okay, so let's shove all these forces by red. So on this member I'm having a compressive force on this member, so that is equal to 40 kilonewton. So I'm having a compressive force here, okay, and that is equal to, oh, that drawing was not so good actually, so let's try again. So this particular force is equal to 84.9 kilonewton, and then these ones are unknown forces, F, D, E, and this particular one is our second unknown force written at this joint, F, D, C. So essentially I'm writing equilibrium equations on this particular joint. Okay, so my assumption is that this joint is a pin. Okay, so there is no moment equation that can be written here, right? Okay, so let's go ahead and write the equilibrium equations for our joint. Okay, so the equilibrium equations for okay, so some of the forces in the y direction will be 0. Okay, and then I'm having this 45-degree angle and the x and y components of this inclined forces. So FDC here, FDC times sine 45 degree and minus 40 kilonewton and minus 84.9 times sine 45 again, sine 45 degree, that is equal to 0. And this equation gives me FDC equal to approximately 141 kilonewton. Okay, and for the sum of the forces in the x direction, on the other hand, is equal to 0, and I'm having the x components of the inclined for 84.9 kilonewton times cosine 45 degree plus FDC, okay, 141 FDC, so that's FDC, and that's the x component of FDC, so 141 times cosine 45 degree and minus FDE, which is this one. Okay, so that will be equal to 0, and this equation yields FDE is equal to 160 kilonewton, and that's compression. Initial assumption was that this is compression, so I find a positive result here, which makes FDE compression. For FDC, my initial assumption was that this is tension on the joint, so making the applied force in the form of tension on the element. So that is a tension. Okay, so we can make a summary of all these results now. So what I will do, I will copy and paste the above figure, this one, I just copy and then go down, and I will paste it here. Okay, so let me just paste it here. Success. Okay, good. So on this I'm going to write the results, so with a red pen. Okay, so here I see that FDE is a compression member, so that's a compression member, and the forces would be like that. Okay, so my FDE is in compression. Sorry, that's tension, by the way. Okay, so the effect is the effect should be tension, compression. So this force is under compression, like that and like that. Okay, from both sides, and this FDE is 160 kilonewtons. Okay, right, and for FDC is 141. So this is FDC, that's in tension, so tensions will be green. So this member is in tension. Okay, so it's not so visible here. So these are like tension, and it's a tension member, and the value FDC is equal to 141 kilonewton. Okay, and going up, I'm having let's see, FBC 60 and FBC 60. So FBC 60 and tension, so this particular member is under tension here. Okay, so tension and 60 kilonewton, right? And let me just, let's see, FBC is in tension, FBD, so this one is under compression force. So BD, element BD is under compression, so it's kind of compressed. Okay, so it is under risk of buckling like that. Okay, so it's compressed. So this is compression, and my FBD is equal to, if BD is equal to 40 kilonewton. Okay, and my FAB is 60, and it's in tension. FAB, so this one is under tension, so that's under tension. So that tension FAB is equal to 60 kilonewton, and finally FAD is 84. Let me see, FAD 84.9 in compression. Okay, so using a red pen, my FAD here is under compression, FAD. Okay, so that these forces are compressive forces, and that FAD is 84.9 kilonewton. Okay, so as you can see, this whole truss, if you look at globally, under this force and this force, so it tries to kind of bend downwards. Okay, like that. Okay, so these members will be going down, and like that, and like that, let's say like that. Okay, so this particular red members will be under compression like that, and the top cord will be under tension. You can visualize maybe, yeah, so it's bending downwards. So the top cord, FAB and BC, will be under tension. So the diagonal FAD will be under compression, the bottom cord DC will be under compression, and the middle or vertical one will be under compression, and lastly this diagonal one will be under tension. Okay, so this explains, kind of justifies our findings. Okay, so this concludes the solution of our problem. Thanks for listening.